Kia ora and welcome. In today's webinar, John Drury and Stephen McNeil will present research and results from an Our Land and Water National Science Challenge project, which explored ways to link soil quality, water quality, and land valuation data to better understand the impacts of land management. We had hoped that Rich McDowell would join us online for this presentation, but he's been called away to other meetings. But one of the benefits of the challenge is the close working relationships developed. So John will be able to present the water quality slides on Rich's behalf. John is a senior researcher in soil physics, and his work encompasses soil quality and the processes affecting water and nutrient flows in soil. Stephen is a geostatistician. I was worried about saying that, I got it out, and his expertise supports a wide variety of projects at Manaaki Whenua, where we draw on his expertise in spatial and time series modelling of environmental properties. I'll be back at the end with your questions, so don't forget to pop them into the question box as soon as you can. But for now, over to you, John.
Well, thanks, Christine. Firstly, welcome everyone, and just like to acknowledge the people that helped with the project and the co-authors. Rich and Stephen have been introduced. Richard Law helped with a lot of the land valuation data and various spatial data processing. Brian Stephen helped with many aspects of the project. And the story map, which we'll talk about, was put together by Zach Hind, Kim Tregurt and Andrew Cowie. I'll give you a bit of an overview in terms of background aims and the key take-home messages. So this will give you a bit of an understanding in terms of what's to come before we get into a bit of the detail. Stephen will talk to you about the data and the statistical modelling in the project. I'll then talk to you about the soil quality and land use pressure results, an overview of the story map, and particularly some of the water quality information as a lead into the results of soil quality, land use pressures and water quality. And first, a bit of background. We were particularly interested in soil quality, and this has been used to evaluate land use intensification on water quality, but particularly at local scale, such as plot scale, paddock and farm scales, but generally not at catchment or national scales. And we were interested in land use pressures. These are things like stock units, particularly land value, and these have been related in the past to things like land use intensity, but these are now publicly available across the whole country. Particularly, we were interested in land value, and we wondered if it could be used as an indicator or proxy of land use pressure. So we wanted to investigate that. It's publicly accessible, it's well defined, and it's routinely estimated. So think of your rates bill there. And it hasn't been previously looked at in terms of environmental work, such as we're doing in this project. Soil and land value are measured at farm scale, and so they may also reflect changes in management practices. So we wondered if could these factors with catchment and climate characteristics help explain catchment water quality trends. So we had a couple of questions. What relationships exist between land value, soil quality and land use or land pressure indicators? Some examples there. And can linking land use pressure and soil quality help predict water quality? So really there's two components of this project. So our aims were to link soil quality indicators to indicators of land use pressure, particularly land value, but also linking all of these to median water quality for the past 15 years. And really just to give you the key take-home messages so that you can put these into context for the bit of the detail that follows. Two components, the soil quality and land use pressure. And overall, we found that soil carbon, phosphorus and bulk density had a highly significant effect when we tried to predict land value. The other soil quality indicators, dominant land use, stock units and catchment characteristics had little effect in predicting land value. So in terms of the second component, the water quality, the state and trend of water quality was strongly related to land use, catchment and climate characteristics, and water quality relationships with soil quality and the land use pressures were not very strong. So I'll now hand over to Stephen and he'll talk to you about the data and some of the detail of the work.
Thanks, John. The data for this study comes from a number of different sources. The main responses are water quality analytes. This is up to 15 years of these properties. That includes things like total nitrogen or visual clarity, for instance. Generally sampled every 28 days, but there are exceptions, and there are long time series and short time series as well. The sampling locations come from a number of different sources, and we're interested in those catchments that hold also some soil quality data. So that's 192 catchments, and that's about 20% of all the catchments and about 31% of the land use area. Soil quality itself represents a range of soil properties that have been sampled since 1995 by regional authorities, and the type of properties that are measured varies greatly, can be up to 85 different properties, but we chose 6 key properties that were common amongst all of the regional authorities. Land value is a novel addition here, and we use property valuation data that includes a ratings unit and also an improvement value. And the primary interest is to see whether this is a surrogate for intensification. Land use itself comes from the land cover database, which is a land cover information, as well as Assure Quality's Agribase and some information from the QE2 National Trust boundaries as well. And this forms 8 land use classes as proportions within each catchment, nominally as of October 2022. And lastly, the livestock type and stocking rates were obtained from Agribase farm locations and the Agricultural Production Survey, and these were combined to give stock equivalent units from within a catchment. On the next slide. On the left, you can see an example of the catchments that we use. These are a subset of all of the catchments. Here, the catchments are coloured by the number of soil quality samples that are available, which vary from very small number to quite large numbers, up to about 86 per catchment. And on the right-hand side, you can see an indication of the revised land use classification that we used. And on the next slide, you've got the land value. And there are a lot of practical difficulties in defining land value. Some areas have no defined value at all, and then a good example are national parks. So in respect of the issue here, which is to try and understand how it could be used as a surrogate for land intensification, it makes sense to assign a very small value, but not a zero value, to natural areas. Some areas have no data available at all, and you can see them in the plot with grey. And the constituent data itself is quite imperfect, so a lot of cleaning was required to get it into this spatial form. Now, catchments cover quite a large land use area, so the association between the value and intensification is quite diffuse, so we wouldn't expect it to have a temporal component. So the key question, as we've noted before, is whether land value is a viable surrogate for intensification. Okay, and the next slide. So the characteristics of the water quality data are that it's essentially an irregularly sampled time series, and it has both seasonal and long-term behaviour. Sometimes the long-term behaviour is secular and increasing, sometimes it increases and decreases, and sometimes there's no obvious variation at all. So the behaviour tends to be catchment specific and obviously moderated by the overall effect of land use, soil and land value, etc. So we don't have a good idea of the effect of land value and soil quality data in association with all the other covariates. It's the combined effect that we want to try and untangle. So essentially there are 2 types of analyses done in 2 different ways. One is a time series analysis where we try and understand how the different analytes change over time in the context of all these other covariates. And the second is how to understand the relationship between the different covariates themselves. For the time series analysis, it's really necessary to use some kind of semi-parametric model that can adapt to the characteristics of each of the catchments, while also simultaneously incorporating the effect of the covariates. So the method we've chosen is the generalized additive model, which is a semi-parametric technique which exhibits great flexibility. The price that you pay for that flexibility is that the computational burden is very much higher, and so we make extensive use of the NESI high performance computing facility as a result. The soil quality and land pressure modeling, which is used to try and find the associations between the different covariates, is a relatively straightforward task that uses a simple linear model. Okay, back to you, John.
Good, thanks, Stephen. So I'm just going to give you an overview of some of the soil quality and land pressure results, particularly related to land value. So some of the covariates that Stephen talked about, these are things like soil quality measurements, carbon, nitrogen, pH, etc. And in terms of catchments, these are things like rainfall, variation of rainfall, catchment slope, elevation, and so forth. So in terms of the key results with this part of the project, we found that soil carbon concentration, Olsen P, which is a measure of plant available P in pastures and crops, and soil bulk density had a highly significant effect in predicting land value. The other variables, including various soil quality ones, you can see there in the diagram, dominant land use, etc., they didn't have a significant effect on predicting land value. And the reason we wanted to look at some of these things was relating some of these things to water quality, as you'll see a bit later on. A wee bit more detail, so we looked at things in a slightly more complex way. Soil carbon concentration, it had a positive relationship with land value, which is quite plausible. Soil bulk density, it also had a positive association with land value, and again, when you think about it, quite plausible. But we found that Olsen P was associated with a reduction in land value, which we didn't really expect, and we haven't really been able to explain that. And there were some interactions with land use, for example, bulk density, exotic forestry, and carbon and exotic forestry. But also Olsen P and dairy, and soil carbon and dairy land use. There were some significant relationships there. And we found that generally the modelling that we did, particularly of high land value, was pretty good, but it wasn't particularly good for things like low land value, so perhaps a bit of work in the future there. So I'll just introduce you to the story map. So the story map was a way of putting together a lot of information, and particularly in terms of some of the water quality variables. So as Stephen had pointed out, there's a number of water quality indicators. There's actually 9 of them. When you multiply that across 192 catchments, it's getting close to 2,000 graphs. So what we decided to do is present some stuff for catchments around the country. So you can zoom in, look at catchments that you're interested in. Here's an example near Masterton, and you can get things like water clarity, turbidity, nitrogen, phosphorus, and so on, and they're listed on the left-hand side of the diagram. You can work your way around the map, click onto the various screens, scroll down, and you'll find some of these images. And just a bit of explanation, the water quality variables over 15 years collected from the councils. We were particularly interested in the long term. So that's the sort of brown wavy line, but we also had to take account of the short term or seasonal variation. And that's what's depicted in the graphs. We'll look at that in a bit more detail later. Here's further information on some of the catchments. Again, bearing in mind these are catchments where soil quality information was available. This diagram shows water quality. And we've got some frequently asked questions and a bit more detail for those that are interested. But back to water quality now. This is an example of total nitrogen in one of the Waikato catchments. Again, just to emphasise that we were particularly interested in the long-term trend, but we did need to take account of the seasonal trend as well. So Stephen's done a huge amount of work there. Another example, black disc, which is an indicator of water clarity. Some of these indicators were difficult to model, resulting in a few issues. And we found that very small values can be poorly modelled, and there was some irregular sampling which can lead to a few issues. This example was data for the 15 years, but for some catchments, data was shorter. But again, general conclusions for this type of approach, the long-term trends were stable, and that's what was important in our work. An example, across all the 192 catchments, we looked at land use effects on the water quality parameters. Here's one, for example, for turbidity. So you can see that increasing the proportion of dairying or dryland grazing, sheep and beef, deer, etc., in the catchment, you can see that turbidity increases. But the converse is true for things like exotic forestry, horticulture, and cropping. And this slide here is sort of a summary of the whole project. And it basically puts the relative importance of some of these indicators that we've talked about on water quality. So further to the right, it implies that there's a more influential effect of some of these indicators. And the water quality responses, the relative importance of water quality was particularly land use and the catchment characteristics. In contrast, the soil quality, stock units and land value had relatively small importance, and you can see that there in the graph with the cluster to the left, and the various indicators there for water quality. So there's a bit to take in, but these slides will be available later on in the link that Christine sends through. So really just to finish off on some of these bits and pieces. So it's truly a sort of a cross-domain project. Here's the influence of soil quality on some of those water quality variables. As you can see, most of them were significant, but Olsen P and bulk density were more likely to be non-significant. This slide shows for many of the catchments how the modelling went, how it explained some of the things that we were interested in. So the modelling approach explains a moderate to high proportion of the variation, particularly for nutrients, dissolved phosphorus, total nitrogen, ammonium N and nitrate N were well explained. Things like E. coli and black disc were only moderately explained. The soil quality variables, they do have an effect, but there are a few obvious patterns. As we mentioned, several of those tended to be non-significant. But in terms of overall messages, the significance for some of the land pressure variables, the land value, stock units have a highly significant effect, but as we saw previously, they had less importance. And the catchment characteristics and land use had a highly significant effect. So overall conclusions, soil carbon concentration, Olsen P and bulk density had a highly significant effect in predicting land value, but the other variables did not. The state and trend of water quality was strongly related to land use, catchments and climate characteristics, things like rainfall, as we've mentioned. And although significant, the water quality relationships with soil quality and the land use pressures were weak. So we thought that national soil quality is useful for evaluating environmental risk at the field and farm scale, but we concluded without a large increase in sampling time-wise or spatially, that they were not that useful at the catchment scale for this purpose. So what does that mean? Overall implications: land value is a unique indicator associated with land pressure, in other words, agricultural intensification. So we use a snapshot in time. We tried examining the land value over many years. It may well be useful in the future if some more work was developed. Increasing the frequency of land use pressure indicators and soil quality data points may improve some of these predictions and work. And remember, we just use a snapshot, and there may be other data available. Soil quality may be unrepresentative of some of the land uses or the hydrologic flow paths to rivers, so further work could be developed from that. And to inform water quality management via these types of soil tests, some additional analyses would be needed. There is some further information. We have a newsletter to stakeholders called Pataio. You can see the image there and click through it. There's lots of information from recent programs on SMAP in various areas around the country, urban soils, nutrient loss, and some of the work that's being done on the Lincoln University dairy farm. So click the link, have a look. We'll be publishing this work in a journal. It'll be submitted soon, so keep an eye open for that in a few months' time. And the story map link, Christine will include that in an email that'll follow this presentation. And lastly, I'd just like to acknowledge all the people that have contributed and the organisations. We'd certainly like to thank the regional councils, the Land Monitoring Forum for the soil quality data, and remembering that some of that was used from the National Environmental Monitoring data set, Headway Systems for supplying the land value data, the regional councils, and through their LAWA website, and NIWA for the water quality data, and Stats NZ for the stocking data. We'd like to acknowledge the use of the eScience infrastructure, or NESI, that's the supercomputer that was needed for this project, given the large amount of data, but also their technical support. And finally, I'd like to thank Airland Water for funding this work, and also co-funding was available from the Soil Health Program funded by MB. And if you've got any queries, do feel free to contact us. Thank you very much, and over to you, Christine.
Thanks, John. Thanks, John. You've obviously provoked quite a lot of interesting questions here. We're not going to get through them all today. But rest assured, if you've popped a question into the question box, you will get a response from us, and we will publish all responses to all of the questions for those of you who found them interesting. There was a quick question around land valuation data. Maybe this would fall to you, Stephen. Is that land valuation data fit for this purpose?
Well, it's fair to say that the land valuation data was really not intended for this use specifically. So we were really testing it out in a new way. And it's fair to say we needed to massage the data to make sure we understood how it worked and to give it a reasonable spatial representation. So I guess the answer is that it probably wasn't intended for this use, but we feel that it's reasonable in the way that we've manipulated it to give a reasonable representation of what we understand as valuation for intensification.
Great, thanks. Now, I'm not sure who might be able to tackle this one. Do you infer a causal relationship between land value and soil characteristics, or is it simply a correlation?
It's an association rather than a causal relationship. So we don't do causal analysis here.
Great. Thanks for that. Anything that you would want to add to that, John?
Yeah, I suppose just reiterating Stephen's point in terms of using the land value data. It's widely available now, and we thought, it could be used as a future indicator, given that it's widely available, it's accessible. So we really, I guess, this way of dealing with the data and looking at it was the first time this has been done, and we tried to use it as a proxy for intensification. But yeah, as Stephen has pointed out, there were a number of challenges. Thanks.
And this question might be just a little bit of a deeper dive into that. So apologies if it's not helpful, but one of our listeners noticed that bulk density is positively related to land value. Does that mean it's good to compact the soil?
Or generally, a lot of the work that's been done suggests that it's not good to compact the soil. But bearing in mind the way we looked at things in this project was at sort of quite a high level rather than some of that sort of detail. So generally, I'd say no, it's not necessarily good to compact.
It's also important to remember that bulk density is associated with changes in soil type, so the association may be rather diffuse there.
Yeah, and that's a good point, Stephen. So one of the things that we did not look at in this project was detail around soil order, but that's a possibility in the future. Thanks.
So this is a topic that has had many other studies, over several years, looking at models that attempt to relate land use, slope, rainfall, and etc. to water quality in particular. Have you done some analysis as to how your results compare with other previously published results?
Yeah, that's a very good question, actually. Richard McDowell would be best to answer that question. However, in some of the information he's done on this project, I noted that there was probably about a 10% improvement in being able to predict some of the water quality variables in the approach that we've used. For some water quality parameters, there was a bit more than that. So I guess I'm suggesting that, there's sort of incremental gains in the way in which we modelled water quality in this project. But yeah, if you'd like further detail, do feel free to put that in the chat, and we'll get Richard to answer that. Thanks, good question.
Just from my perspective, each new modelling effort that's gone on with this type of data has added more and more complexity. And so, as a collective of science in New Zealand, we understand more about the subject as a result. And I imagine that people will look at some of the things that we found and say, oh, well, we can add another variable into it and elaborate the model even further. So that's the way the science works.
Great. Thanks for that. And I'm just going to finish off with the fact that we sometimes get answers from our audience as well. And Eric's dropped a little note in here to say that he thinks it's not soil density that leads to high land value, but that the highly valued land tends to get compacted through by being overworked, as it were. Look, thanks everyone for comments and questions. A special thanks to John and Stephen for presenting in such a short space of time a very complex topic and some a little insight into all the works below the bonnet of this work. We really appreciate your time and look forward to welcoming you all again to another LINKOnline webinar next month. Bye for now.